So, Thomas.
Thank you very much, Tom, for the nice introduction. Thank you all for attending the lecture and for wanting to learn and hear about my work on essentially trying to understand how we characterize recombination in perovskite solar cells. So it's connected in terms of the technology with the talk that we heard from Eugene. So it's about the same type of solar cells, but it's now focused not on stability as before, but on the topic of recombination, how that affects efficiency and how we measure recombination in these types of devices. So the outline of my talk is shown here. So I'll first talk about the concept of charge carrier lifetimes. So that's not the lifetime of the module or the solar cell, but really the lifetime of the charge carriers, which is on the order of microseconds. And I'll talk about why this concept and this term lifetime can be quite problematic, because it's just different people mean different things. So this is the main problem here. Then the second part will be about how to interpret the data that we get on different types of experiments, mostly transient photoluminescence as a experiment that is very frequently done. This will involve a couple of equations where I hope I'll bring them to you in a way that you can understand them. And then I'll talk a little bit about shallow defects. So I'm not sure they're the same defects that you see in PDS and FTPS measurements in the band tails, but maybe they are. And why I think we can also see them in our photoluminescence transients. Okay. So at the beginning, I want to talk a little bit about the current voltage curves, especially for those people who don't look at solar cells and current voltage curves all the time. And one thing that I find many people at the beginning find very confusing is the different bias points that we've seen. Different bias points mean different rates of degradation, but they also mean differently shaped band diagrams, right? And different ways of plotting the Fermi levels and so on. So this is one of like a schematic of a typical perovskite solar cell. Like we did that, for instance, with it's called an inverted structure, where you have the hole contact at the bottom and the electron contact at the top, and the light would come here from the bottom. Now this is a typical current voltage curve that you see here, and here you have the three main bias points that Eugene has drawn on the blackboard. So that's short circuit, maximum power point, open circuit. And if you want to explain how a solar cell works, you can now start with a single photon and see what happens, right? And then you have your single photon, and the photon will create an electron hole pair, each of the three situations, and then the electron hole pair will be collected at short circuit, and will also hopefully be collected at the maximum power point. And at open circuit, it of course will not be collected. So open circuit is this situation here. Here it can't be collected because open circuit is when the cables are hanging in the air and are not connected, right? So how can I explain open circuit? I can't really explain it with one photon and one electron and one hole because nothing is really happening. So I need a different picture. And so this is what I try to explain open circuit. So we have this schematic of our solar cell, and then we have a continuous illumination, and this continuous illumination continuously creates electron hole pairs, right? And then at some point, there will be a balance between the electron hole pairs being created. We can explain that with the generation rate here, and the electron hole pairs recombining. So in an ideal case, they recombine and give out a photon again, so that we have photon in, photon out being perfectly balanced out if we just count the photons. Not the energies, but the number of photons per time, right? Okay, so I can only explain the open circuit situation with many photons and some steady state condition that is created, right? And so a very simplistic way of explaining that in equations would be to say, okay, the average rate of generation rate is equal to the average recombination rate. And then many people at this point would write the recombination rate as carrier density over, now the tau comes in. This is our lifetime that we'll talk about a lot later on. And the lifetime would then have something to do with how quickly these electrons and holes recombine, right? And from this balance of generation and recombination, you could then calculate the maximum open circuit voltage you could get inside a solar cell if you relate your carrier concentration with a voltage. Yeah? So this is the step that you have to take to get to an open circuit voltage. And the general idea is that, you know, the open circuit voltage has something to do with how many charge carriers you have in this balanced out situation between generation and recombination. And depending on whether you have an intrinsic or doped semiconductor, you have a different relation between carrier density and voltage. In perovskites, they're very lowly doped. So I assume electron and hole concentration are the same, and then we would get this exponent Q VOC over 2 kT term here, yeah, to relate the electron concentration to essentially the Fermi level splitting. And so the maximum VOC you could then get, you could solve this equation, would then be 2 kT over Q times the natural logarithm. And now here comes the electron density, and here the equilibrium density, and the electron density would just be generation rate times this lifetime. Yeah, so this is a relatively simple math that is aimed to motivate why this charge carrier lifetime is an important quantity, at least at first sight, right? So it tells you, okay, if I illuminate my solar cell with a given generation rate, yeah, and I have a given band gap that sets this Ni here, then if I have a very long lifetime, I should be able to get a higher open circuit voltage, right? This so far so good, right? Okay, and this is why people are very interested in this concept of a charge carrier lifetime. Yeah? And so this would be this current voltage curve you see here. That would be a situation with a very long lifetime and a high open circuit voltage. And then if your charge carrier lifetime was lower, yeah, you would get a smaller open circuit voltage. So your curve would just be shifted to the left on this axis, and you'd have a smaller difference between these two Fermi levels for electrons and holes. Okay, now this is how it should work, yeah, and this is why people are interested in the concept of a lifetime. Now I start with the problem. So far there's no problem. It's just a little bit of math, right? Okay. So the problem comes at this point. It's a very fundamental, problem that goes into the philosophy of science to a certain degree. That's why I think it's interesting for the Landsberg seminar. So the problem starts with the scientific process. You always start with a hypothesis. Yeah? My solar cell is bad or my solar cell is good could be a hypothesis. Yeah, and then you start an experiment. You make a solar cell, measure it, right? And then there, from having your experimental data to having some sort of information, there is an intermediate step, right? And this intermediate step is usually in many cases, where the trouble begins. Yeah? Let's assume you have a nice experimental setup and it's working, it's not broken. Yeah, then that's where the trouble begins, right? It's the analysis of the data and the interpretation of the data, right? And in many cases, the interpretation of the data is kind of done, for instance, by an empirical model, maybe an empirical fit. Yeah? So in the world of lifetimes are often measured by fitting exponentials to experimental curves. Yeah? So you have an experimental observable, maybe a photoluminescence decay, and then you fit an exponential curve to this decay. Yeah? So this is what I would call an empirical fit. Yeah? Sorry, this button here. Yeah? And then you get something out and you call it a lifetime. And now the problem comes that different people mean now different things because they fitted different exponents to different things. Yeah? And at the beginning, this may sound like a minor issue, yeah? But I'll tell you this is quite a major issue when you try to learn something, yeah, from your fits. Okay, and to illustrate why this is a major issue, I have this, this plot that looks like lots of random points. Yeah, it looks like not very pretty at the beginning, right? And so the thing is, what you can see on the y-axis is lifetimes that are measured by just taking a solar cell, hitting it with a laser pulse, and plugging the two ends of the solar cell into an oscilloscope. Yeah? And then it's called a transient photovoltage decay measurement. Yeah? usually you do this as a certain bias point. Yeah, you keep it at some VOC, and then you add laser pulse and just measure the voltage in an oscilloscope and fit an exponential to it. Okay, and then you can get lifetimes from that. Yeah? And on the x-axis, you do the same thing, but optically. Yeah, hit it again with a laser pulse, and measure the photoluminescence coming back from the sample, fit an exponential to it, and plot that number. Yeah? And now each of the points represents one paper. All of these papers are from, how shall I call this, respectable journals. Yeah, so like Nature, Science, Daily Mail. And then you can take each of these points. So if there's a point here, then it means somebody measured 10 microsecond PL lifetime in a paper, and then approximately also 10 microsecond TPV lifetime in the same paper, and that's fine, I guess, right? There's nothing wrong about this. If there's a point here, then it means that somebody published a, I don't know, nearly 3 microsecond PL lifetime. And in the same paper, they also published a, what's that, something millisecond TPV lifetime, and didn't talk about it. Yeah, just said, okay, that's our lifetime. And this is where the problem starts, because now what is a lifetime then? Yeah, if they're like so many orders of magnitude different. Yeah, I mean, okay, this is on a cell. Yeah. Yeah, there should be a consensus on how to measure lifetimes. But obviously, so the authors of this paper, they must have meant something different when they measured this lifetime and when they measured this lifetime, yeah? Because it's completely different numbers. Yeah? So this lifetime on the y-axis, that's on a cell, and the lifetime on the x-axis, that's on a film. So this is obviously already a difference. But why on earth would the lifetime of the cell be 3 orders of magnitude longer? Yeah, it certainly doesn't have 3 orders of magnitude less defects. Yeah, that I can assure you. So it must be something else. Okay, and this is when I started to get interested in trying to understand what on earth do people mean. And now this is what I think can already solve the problem. It's just a really minor addition to this process. So you take your experimental data, and then you don't do an empirical fit, but you think about some sort of model. Yeah, and the model should not be entirely empiric. You need to think about it first, and then think about what a sensible model is, and then try to extract not something that you just call a lifetime, but you extract some sort of parameters of a model that have a physical meaning that you can explain to somebody. Yeah? This is a very minor addition to the process on the left, but it can help a lot in understanding things. Okay, now let's come to our study that we tried to do on this. So I'll show you different sets of experimental data in the following, and many of them were taken in this logic. So we measured mostly transient photoluminescence and a little bit of transient photovoltage for comparison as well. And the photoluminescence in a perovskite solar cell, or in any solar cell essentially, is proportional to the product of electron and hole concentration, because you need 1 electron, 1 hole to make a photon, right? And because the perovskites are so intrinsic, this is the same as saying it's proportional to electron concentration squared, to a pretty good approximation. Okay, and then you can do this, because it's a purely optical technique, photon in, photon out. Yeah, you can do this on films, on glass. You can do this on films with 1 contact, with 2 contacts, or 2 transport layers, and complete devices that have 1 metallic contact and 1 ITO on the other side. Yeah? So, and then from left to right, it gets all more and more complicated, because more and more things are happening. But it's exactly these things that make it complicated, that you need to understand in order to don't plot completely strange lifetimes. Okay, let's start with the simple case, or the simplest case, which would be film on glass. Yeah? And here you have typically 2 types of recombination mechanisms that are particularly important. So one is defect assisted, just some people call that Shockley-Rittal recombination. and the other one is just radiative recombination. Yeah? So the radiative recombination is important for two reasons. First, it's your observable. Yeah? It's the thing that you actually measure at the end. It's the photon that comes out of this radiative recombination process. But second, it's also affecting your carrier density that you have, and thereby the time dependence of your photoluminescence. Yeah? The non-radiative recombination is not your observable, but you still see it because you see the carrier density going down from getting less photons out. Yeah? So this is what some people find very confusing at the beginning when they look at photoluminescence. Yeah? So it's really the radiative recombination is your observable that you measure, but you see all kinds of recombination processes because they all affect your carrier density. Okay. And then if you write down a differential equation trying to explain how n depends on the time, then you have essentially these two terms that make n go down. One that is quadratic in n and one that is linear in n, if it's a deep trap at least. And if you then measure something, it would probably look like this. Yeah, so you have at the beginning, your quadratic recombination term is dominant, and at later times, your linear term becomes dominant, and then at the beginning you have something that's not exponential, and then towards later time it becomes more and more exponential. Okay, so one way of now plotting this data is not to plot the raw data, but to plot the differential of the data. This is something I'll do a lot in the following slides, and I found it quite useful to understand things. So that means you just take the negative logarithmic derivative of the photoluminescence with respect to time and take the inverse of that, which sounds very complicated, I know, but this is then what will give you, for a mono-exponential decay, it will exactly give you the thing that we call a lifetime, which is this, the sum of the two Shockley-Ritol lifetimes, tau n and tau p. That's what you could call a lifetime from a model perspective. Yeah? And this way of plotting the data will give you exactly that lifetime at low Fermi level splittings, yeah? So low carrier densities, and at high carrier densities, it will give you something that's not constant, and this part is then due to this radiative recombination term here. Okay, so this is kind of modeled data, and we'll now in the following look at experimental data. And we'll now also look at transient photovoltage. So here you see a schematic of the setup that we're using for this. So with a pulsed laser, we have a solar cell or a film, yeah, but solar cell is the more general case. And then the solar cell will have a photoluminescence that we detect with a gated silicon CCD camera and then plot as a function of time. But the solar cell will also create a voltage that we will measure with an oscilloscope and have this voltage decay here. And then we can measure with the same setup at the same time transient photovoltage and transient photoluminescence. Okay, now this is how real data looks like. If you do this, and if you're sufficiently patient and measure for a sufficiently long time, you get really nice dynamic range of up to 8 orders of magnitude here. Yeah? And the gray data is the film, and the red data is perovskite solar cell. Okay, and now on the right, you see the same thing, but plotted in this way that I explained before as a differential decay time. Yeah, I use the word decay time to make sure this is the experimental, like a time that is derived from directly from the experimentally observable data. And lifetime is now everything that is really interpreted, because I want to distinguish between the experiment and the interpretation of the experiment, because this is exactly where the problem starts, right? Okay, and now the gray is the film, and you can see it's continuously changing for as long as we can measure. That means it doesn't seem to have any deep trap that is visible in the data. Yeah? It's really continuously changing. So you don't get one decay time, you get decay times that vary from tens of nanoseconds to tens of microseconds. Okay, and then the film shows something different. It shows a similar effect at the beginning. Then it has a plateau, and then the noise starts, but it goes up a little bit. Yeah, but it's already getting quite noisy here. But this seems to actually have a plateau, which indicates some sort of Shockley-Ritol mechanism that goes approximately linear with carrier density. And then you see the TPV data, which is the stars, and the TPV data, it's on a cell. It actually is not too far away from the film data, the solar cell data, sorry. Yeah. Okay, so that seems to make sense. Now the question is, can we explain this? Okay, now, of course, you can do full-fledged drift diffusion simulation of everything if you like to do this, and we also did that, but that was loads of work and not particularly instructive. So we tried to find a more instructive way of explaining the data, and I know it's a differential equation again, but I think it's actually not super complicated. So the only thing that is changed here relative to before, yeah. So this is the differential equation that we need to understand how the carrier density changes with time, and it's got two terms related to recombination, radiative and non-radiative, and it just got one extra term. Yeah, this is for the bias light and the TPV. That's not so important, but this term is important. So this is capacitive charging of the electrode. So that's a term that only exists in the situation where we have a solar cell, not for the film. But for the solar cell, it exists because the electrons going to the electrodes, yeah, and then they're also coming back from the electrodes, and that can cause a very long lifetime. And I'll show you what these terms do. Yeah. So we can, from this differential equation, you could try to solve it for n of t, yeah, but that's kind of relatively tedious to do. It's a really long equation. That's not very nice. It's easier to directly solve it for the lifetime, yeah, or the decay time. So for this logarithmic derivative, yeah, because you can see this is a logarithmic or an inverse logarithmic derivative, the ln n dt, yeah, and this is something you can directly get from this if you find a relation between the voltage and the carrier density, which you can just do with an exponential. And then you get something relatively simple, yeah, where you have the recombination terms in the denominator here, and here you have in the NQ you've got the influence of the capacitance of the electrodes hidden. Yeah, and the equation, okay, it looks a bit complicated, but it's not actually that bad. Yeah. Okay, now I highlight the different terms. So this is where the capacitance goes in. It's here, and in this equation, the capacitance, so this re-injection of electrons from the contact, that's the thing that causes this part of the data. Yeah. So this leads to these very long lifetimes at low carrier densities of Fermi level splittings. Then we have the radiative recombination. This leads to this part of the data, yeah, where at high Fermi level splittings, where the lifetime or decay time is very short. And the Shockley-Ritol recombination is the bit that gives you flat decay time. So that's the bit in the middle where the inflection point is. Yeah. Okay, so let's come to the interpretation of this and to the interpretation of our original problem. So why are there so many points that are miles away from the one-to-one line? So my interpretation is that is because the TPV measurements are very often done in this regime, which means for smaller bias light intensities, you're very often in the regime where you're in the capacitively limited situation where, you know, it's the re-injection of electrons from the electrodes, which is a very slow process and limited by the capacitance of the thing. And that gives you really long decay times that are not lifetimes, not in any sense of the word lifetime. Yeah, and so the TPL, usually you do that at higher laser intensities because that's when it's easier to measure, right? At higher laser intensities, and so you, even if you do it on a cell, you wouldn't necessarily see this. Yeah, and so you generally get shorter lifetimes from the transient photoluminescence. Yeah, and it's just because the decay time is not a constant but changes over orders of magnitude, and different measurement methods probe different parts of the decay, and not all of these parts are even related to recombination. Yeah? So this is kind of the key problem that causes these issues with this figure here. Yeah? Okay. Yeah. Okay. So just going back to what we learned about our sample, yeah, because some of you may not be interested in the method, maybe more interested in what we learned from the method. So essentially, when we just look at the films on glass, yeah, with and without whole transport layer, we essentially see no signatures of defects visible in the transient. So it seemed to be very good bulk quality, which is also consistent with the very high open circuit voltages that we got in these cells. The interface to the whole transport layer seems to be also relatively harmless or electrically benign, while the interface to the electron transport layer, the PCBM in this case, this is when we go from green and gray to red. So there definitely seems to be some trap at this interface, and that's also consistent with what other people find. So every fullerene perovskite interface usually has a trap sitting there that is not good. Yeah? So we need to find ways of getting rid of the fullerenes or making them less recombination active somehow. Okay, and now I do a little extra study that I hope I'll have time for about the shallow traps. So in the graph before, you've already noticed that one of the key things in order to get to the conclusions we've gotten before was our ability to measure this decay time over a range of carrier densities or Fermi level splittings. Yeah? So if we had only had a really small range of the data, we wouldn't have seen this S shape, yeah? And we wouldn't have been able to interpret the three branches of the S. Yeah? So the radiative part, the Shockley hole part, and the capacitive part. So you need some sort of dynamic range to see all of this. Yeah? But the problem is, in many cases, people measure with setups that don't really allow a large dynamic range. And so this is a graph where we've plotted the dynamic range that people report in TRPL measurements versus the decay times or lifetimes that they report. And so the overwhelming majority of reports is in the, say, 2 to 4 orders of magnitude dynamic range bit. Yeah? And only, this is the work we've seen before. Yeah? This was around 8 orders of magnitude, and then our camera was very old, so we bought a new one, and that actually brought us here, yeah, to about 10 orders of magnitude dynamic range. And now it gets really interesting, yeah, and because you also can look now at the y-axis. Yeah? The y-axis now says, okay, this is 1 microsecond, 10, 100, says like something 300 microseconds. Yeah? Nobody's ever said that before. Yeah? But this is actually something that we see, and it's not even something to be particularly proud about. Yeah, but it's interesting. Yeah, interesting from a fundamental point of view of understanding what a lifetime or decay time is. Yeah, because I now claim we can see something like 300 microseconds or something like that. Yeah? And it's only a matter of measuring for sufficiently long. Yeah. Okay, good. And this is all about doing this with this specific setup and this CCD camera. And now let's look at the data. So this is not the 300 microsecond data, but that's at least 200 here. And it's interesting because it just continuously goes up and up and up and up. Yeah? So it doesn't show anything that's flat. It doesn't have any flat component. This is just a film. Yeah? It's similar to the one before that also went up and up and up, but the one before went up with exactly the slope that you would expect for radiative recombination. This is not the case anymore here. This can't be radiative recombination. Yeah? So certainly radiative recombination is what we see. It's the photons we see come from radiative recombination, but the shape of this curve cannot come from radiative recombination. It's got a slope. Yeah? And the slope is actually consistent with the steady state PL slope. And the steady state PL slope, you can calculate an ideality factor from this, says 1.2. as an ideality factor. So 1 would be radiative. So it's definitely not radiative. It's definitely not a deep trap. So I don't have so much fantasy, so I thought maybe it's a shallow trap. Yeah. Okay. So this is the obvious conclusion for somebody like me who's not particularly creative, doesn't want to invent a new recombination mechanism. So maybe it's something like a shallow trap. Yeah. And then we tried to fit the stuff. And then we know that, in Shockley-Rittal recombination, most people write the Shockley-Rittal equation just for deep traps because then it gets nice and simple. But you can, if you look up in a textbook, you get the whole thing. It's not simple, but it has a few more terms, right? And I don't bother you with the equation, but if you add some shallow traps, yeah, if you add one shallow trap, you can get it on this slope for a while, but not for that much. Yeah? If you wanted to get with this nearly constant slope for like 400 millivolts or milli-electron volts in Fermi level splitting, we needed 2 of them. Yeah, because it's always each trap has a transition from 1 to 2, and you can't really have one trap and keep the slope forever. Yeah? So if for 2 traps it worked, and maybe we need a distribution of traps, which is where the tails come in, of course, right? And you can also see for this bit, we'd need probably a 3rd trap. Yeah? But we were too lazy to do this. Okay. Yeah, and then the funny thing is, so just have a look at this equation here. So it's very, very simple. So if you say tau has something to do with electron concentration over recombination rate, yeah? And we're pretty sure our sample is intrinsic, yeah? That means the electron concentration would go with Fermi level splitting over 2 kT. But the recombination rate would go with Fermi level splitting over ideality factor kT. Then the ratio would go with Fermi level over kT times 1/2 minus 1 over ideality factor, yeah? So far, so good from a mathematical point of view, yeah, hopefully. Okay, now let's assume the idea is just to do a test. So if the ideality factor is 2, yeah, then we get 1/2 minus 1/2 is 0, right? So we get flat tau. This is what I showed you before, yeah? Deep trap makes it go flat, yeah? If we have radiative recombination, it's 1/2 minus 1, it would be minus 1/2. So that's the minus 1/2 slope that I showed you before for radiative recombination. If we have here a 1.2, then it's 1/2 minus 1 over 1.2. So that's something that's neither 0 nor 1/2. Yeah, so it's a weird slope, but it also means it's something that is negative. Yeah, that means when the Fermi level splitting goes down, it just continuously increases. Yeah. Do you see what I mean? So whenever you have a non-integer ideality factor, actually whenever you have an ideality factor that is not 2, yeah, then even without having radiative recombination, only the lifetime will change the whole time, yeah, until eternity. So that means the question of getting a very long lifetime becomes at some point only a question of measuring for sufficiently long. Yeah. That's what I want to say. So it's not really something to have it's not a competition of having the best cell on the planet. It's just a question of what is this decay time and then measuring for a while. Okay. And the other interesting thing that I wanted to show you quickly, I think now I'm approximately out of time, is this going from film to cell. Yeah, because you might be interested, okay, that you see that's in a film, but is this even relevant for a cell? And the fact is it is, yeah. And now what you will see on the left is this is always the decay, yeah. Here you can see the dynamic range and the time axis, yeah. So this is a long time axis, yeah. This is 1 microsecond, 10 microsecond, 100 microsecond. And on the right you see this differential decay time thing, and this is 100 microsecond here. Yeah. And now I'll go through it quite quickly. So this is the film. Yeah, this is the film with C60 in red. So it's you can again see the C60 is doing something bad. Yeah, but it's not a complete disaster. Then we go to the steady state. I skip over this. Yeah, Then we go to film on the whole transport layer. This was this self-assembled monolayer Me4 packs here. It's also still quite similar. Yeah, not a big difference, a little bit. And then we go to both transport layers, still similar. And then we go to the cell. Yeah, and the cell, okay, here's a bit lower, and then I guess this is the capacitance. This is the reinjection, I guess, because then it goes into the sky. Yeah. If it's not the reinjection, then it's, I don't know, something else. Noise related, yeah. But the end of the decay is obviously always a bit tricky, yeah, because at some point you hit noise, yeah. Okay, so but the general idea is that this trend of changing and changing and changing and changing, this is something that goes from the film to the cell. It seems to be quite consistently there all the time. The one thing you need to be able to do in your measurement to see this, you need a super low repetition rate in your setup. Yeah? Most people measure with, say, 100 kilohertz repetition rate. Yeah? That means every 10 microsecond there's a new pulse coming. Yeah? And then you can't see this. Yeah? So we measure with 100 hertz. Yeah? It means every 10 milliseconds a new pulse coming, and then you can measure this. But you need like many hours for one of these curves. Okay, good. So this is all of them now. So you see it's not super different. Yeah, on the whole scale of things, it's not super different. Okay, good. So summary. The first part was trying to tell you that actually electrical transients and optical transients, they can fit together. The information you extract from them does fit together, but it wouldn't fit together if you were just fitting exponentials to the data. Yeah? So you need to actually fit some sort of model to it that contains the key features, like the capacitance, for instance. But then it can all make sense. So it's a little addition, a little bit extra effort, but I think it pays off when trying to understand things. And then the second part is, so this was on methylammonium lead iodide, so the traditional fruit fly type perovskite, and this is on triple cation perovskites, and they seem to really be different in at least the position of key defects. Yeah, so this material is not as good as this one in terms of the absolute PL, but it still shows longer lifetimes because this was the newer camera. This is probably the key reason. Yeah, and so with the newer camera, you can just measure for longer, and I think that this continuous change of lifetime with this particular slope is just a signature of more than one, maybe a distribution of shallow defects, and that the explanation of this feature that we see here is probably quite closely connected to the interpretation of these non-integer ideality factors that you see in these triple cation perovskites. Yeah? So here you see mostly 2 as an ideality factor, and here you see something close to 1, but not quite 1. Yeah? And I think this is all connected to each other, and hopefully in the future we'll be able to get this all together. Yeah? So the information on the density of states, the information on the steady state data, and the information on the transients, and make a sensible picture out of it that we can use to explain recombination in these types of solar cells. Okay. So thanks to you for your attention. Thanks to the people who actually did the work, mostly postdocs and PhD students of mine, Uwe Rau always, for coming up with several of the equations. And yeah, hope to stimulate a nice discussion. Thank you.
Thank you very much, Thomas. Yeah, I think I would second the word stimulating, very stimulating talk, and hopefully will stimulate some discussion also, some questions.
So, is it working? Okay, so let me ask first question. How how did you actually evaluate the quasi-Fermi level splitting? Is it just from the illumination, or is it really calculated based on how much you think that there are really really the carriers present in the layer?
Yeah, I skipped over this essentially. So if you just look at the the first point here, yeah. So when this first point here at the highest Fermi level splitting, this corresponds to the first point on the upper left here, yeah. And for this first point, this is essentially directly after the laser pulse, yeah. So what we do is we measure the laser pulse, yeah, and know how many photons are in one pulse, yeah. Then we know how many of them are absorbed, and then we can calculate what our initial carrier density should be, yeah. Then we need one more thing. We need the intrinsic carrier density, right? We need to know what the Ni squared is, essentially, yeah. So we need density of states and band gap and stuff like that, right? But if we assume that this is approximately correct, yeah, then from the knowledge of your initial carrier concentration, you get this first point here, yeah. So you can calculate what you start with, and then from there, every 60 millivolts in this direction, yeah, corresponds to 1 order of magnitude on this axis, yeah, because you know that photoluminescence scales with a Fermi level splitting with exponent exponent Fermi level splitting over 1 kT, yeah. And this is very fundamental. Always works for band-to-band recombination as long as you're in the Boltzmann approximation. And so there's very little that can go wrong. Except for the first point, yeah. Of course, you could do something wrong with your laser power measurement, for instance, and your intrinsic carrier concentration could also be off. Yeah. But if you trust these values, then you can trust the first point, and then if you trust the first point, you can always trust the rest, in my opinion.
So in principle, you measure based on based on the radiation. You measure the carrier density. So you know that that between radiation intensity and the concentration there is a fixed relation all the time. I think you said you assume.
So I mean, I know how many photons are in one laser pulse, yeah? And if I know how many photons are in one laser pulse, I can figure out how many electron-hole pairs my laser pulse has created, yeah? Because I know the absorptance of my film.
Okay,
right?
I mean, this is
easy to understand, right?
No, but this is the generation term.
Yeah.
And the actual concentration is after solving the equation, but but I think we can discuss that later. So my question is, so this is normalized photoluminescence. So because what is quite interesting topic, and I think you must have some opinion on that also, because when you will not normalize, you will see effect called luminescence quenching, and that's, I think, so you will see drop of intensity when you for example put this C60, right? Because or maybe you see increase, yeah. So the question is,
you mean a steady state PL?
Yes.
For instance,
Yes. Basically,
this is this data that I skimmed over. You can have a look at it more closely. So this is all. So this is the. Just look at the red parts. Yeah, the red is the samples that I showed. The black here is a reference, and this is film. And then from film to film on HTL, it actually goes up. Don't understand really why. So apparently, the perovskite grows more happily on the whole transport layer than it grows on the glass, yeah. And then with C60 it goes down, yeah. And then again on the whole transport layer, and the C60 is again happier than with C60 on and glass on the two sides. It's the worst case, yeah.
But that one you just explain as a quality of layer somehow, it's not like, you know, this PL quenching due to the carrier extraction.
No, I mean no. This is steady state. This is steady state PL, right? So if you know, this is measured under continuous illumination. Yeah. So you hit your sample with continuous light, and then at the beginning, when you switch on the light, of course, some electrons will go to the C60 and some holes will go to the Me4pax thingy, and maybe we combine with some electrons in the ITO, right? But then there will be a steady state situation, all flat Fermi levels, yeah? And then it's only recombination that you measure, yeah?
Yeah, I think, yeah, okay.
Jakob, we've got coffee waiting outside, so can somebody else like to ask a question? If possible, quickly, please. Yeah, Martin.
I just wanted to ask if you compare the MAPI and the triple cation. It's on the picture
at the very end.
Yeah, at the very end, exactly. So it means that the MAPI is like almost ideal material, like without shallow traps, and the triple cation is with a lot of these shallow traps, or what's the conclusion?
Yeah, that's
there?
what I don't think that every MAPI is like this particular MAPI. I think that this is a particular type of preparation method with a particular precursor, and apparently that leads to very recombination inactive bulk material, and also very recombination inactive interface to the whole transport layer, but still some recombination activity towards the PCBM. But it doesn't seem to have shallow traps really, because just infer that from this slope, because this slope of the gray data is exactly parallel to the blue dots, and the blue dots is what you would expect for radiative recombination. It's this perfect exponent over -2 kT behavior. And here, on this side, this is a different slope. Yeah, so it's a bit flatter than radiative. So I think it's full of shallow traps. Yeah. Yeah. I mean, of course, this is only one evidence for it. We can try to find other evidences.
So that's the VOC record MAPI.
Yeah, this thing is kind of more or less the same recipe as the VOC record. Yeah. I think it got only 1.25 instead of 1.26, but it's more or less the same recipe. And this one that's for triple cation, it's good. Yeah, it's a 1.2 and a bit volt VOC, but it's definitely worse in terms of the VOC than this one. But it's better in efficiency and stability, unfortunately. Yeah. So it's.
And can you measure the quantum yield of these things, like of these layers?
The PL quantum yield.
Yeah.
So I mean, this one is 5%-ish, and this one is on slide somewhere else. Let me try. No, that doesn't work. It was here. So okay, can't quite see the quantum yield. We need to calculate it. So it's a difference between here and here gives the quantum yield. So it's 0.5% approximately. Okay,
so it's lower.
half a percent. It's an order of magnitude worse, approximately. Yeah. So this is. I mean, this is 120. No, maybe it's 1%. Maybe it's 1%. So this is approximately 120 millivolts away from the red dashed line, and that would be 2 orders of magnitude. Yeah. So 2 times kT ln 10. Yeah. Approximately.
Shall we adjourn? I believe there is coffee outside. Can we make? Please don't go away too much, because we may have to cut the coffee break at 10 minutes, maybe a little bit more, so that we don't run too much into the afternoon. So thank you very much again.